sharing the slide. Is everything okay?
Yeah, you can put it on full screen.
Full screen?
Full screen, better.
The slide. Very good.
Okay, so we are starting the PhD thesis defense of Nicolas Armijo. So let me thank the examination committee. So Paulo Silva from the University of Campinas, Defeng Sun from the Hong Kong Polytechnic University, Nathan Krislock from the Northern Illinois University, and originally it was supposed to be Professor Wolkowitz, but we made a mess with the schedule, so we apologize for that. So we are very thankful for Leandro from the Leandro Prudente from Federal University of Goiás, who kindly accepted such a short notice invitation. So thank you for that, Leandro. So we will start with a 40 minutes presentation by Nicolas, and then the committee will ask questions. So go ahead, Nicolas.
Thank you, Professor. Well, first of all, I would like to thank the presence today. I know it's quite late there in Hong Kong. I know it's Thanksgiving in the United States, so I really appreciate the effort that you're doing today for being here. And I would like to thank my family and friends here present, and also special thanks to my supervisor and co-supervisor, Dr. Gabriel Hasser and Dr. Junior Bello Cruz, for the guidance and the patience all this time. Okay, so I'm going to present the summary of the PhD research here at the University of São Paulo. The work is titled Simple-Newton Method for Conic Projection Equations is related with conic programming. And the presentation is structured as follows. So I'm going to start presenting the main objective of the work. Then I'm going to talk about a little bit about the related work. And then I'm presenting the three big steps that we did here. The first one involving the piecewise linear system, which is a projection equation related with quadratic programming, where we studied proposed semi-smooth Newton method, and we also proposed two alternatives based on the well-known Jacobian Gauss-Seidel Newton method for classical linear systems. The second step, we generalized some results to the now quadratic conic programming, changing the non-negative variables to now general cone, and also additional linear constraints, where we study properties and also propose a semi-smooth Newton method for the problem, making numerical experiments for the nearest correlation matrix problem. And finally, we can address the nonlinear conic programming problem, which is the main goal, where we generalize even more some properties, and we propose a semi-smooth Newton method for it, okay, making numerical experiments for the particular cases of the circular cone programming and semi-definite programming problem. Okay, so the main goal here is to try to solve the nonlinear conic programming problem. This problem consists in minimizing a function f subject to a conic constraint involving a function g and a closed and convex cone k. Okay, both of these functions f and g are assumed twice differentiable. Okay, so there are three main classes solving this type of problems. The first one are interior point methods, specifically the barrier methods, which try to solve a penalized version of the problem using a barrier function, b, and a penalization parameter, t. So the idea here is try to solve the first order optimality conditions of this problem, which approximate the first order optimality condition for the original problem. The second class are the augmented Lagrangian methods, which is another approach. They try to solve the classical Lagrangian function with a penalization function here involving the constraint G, Lagrange multipliers, and penalization parameters. And the idea here is try to solve, to find the stationary points for the Lagrangian method, for the Lagrangian function at every iteration. And the third class are the smoothing methods. And these methods are very close to this work. The idea here is try to solve a reformulation of the first order optimality conditions using a parameter epsilon and replacing the differentiable components with a smoothing function phi. That's the idea. So what are we trying to do? Well, we're trying to solve this system, the KKT conditions, which involves the stationarity of the Lagrangian function, the complementarity conditions, and dual and primum feasibility. So what are we going to do that? Well, the motivation is the piecewise linear system. This is an equation involving a matrix T, a vector B, and the positive part of X. This positive part is well known, is defined as the maximum between 0 and X component-wise, which is also the definition or an expression of the orthogonal projection of X onto the non-negative orthon cone. So what we study in this equation, because this equation, this piecewise linear system, is closely related with the quadratic programming problem. This problem is minimizing a quadratic function over non-negative variables constraints. Okay, so what is the connection? Well, the first order optimality condition for the problem are this one right here, and using the data of this problem, specifically the matrix Q and this vector Q, we can state a piecewise linear system, and it has the important property that the solutions of this equation generates first order optimality condition points for the quadratic programming problem. So this is the connection, and this is the foundation of the research here. So regarding this equation, several properties have been studied regarding existing uniqueness of the solution involving the matrix T and the applied equation involving the matrix Q. But in general, there is no problem assuming the existence of the solution because we are studying this equation related to the optimization problem. So we are assuming they have solutions. So since we have the equation now, and we can recover KKT conditions points, for the problem, the idea is now try to solve it. The first idea is try to use the Newton method. The classical Newton method, try to solve the problem, try to find the zeros of a function specifically, using this expression right here. So where this JF is the Jacobian matrix of the function f at a point. For this case, for our case, the functions involved are not differentiable at every point. The orthogonal projections can be non-differentiable at some points, and therefore we need to use a semi-smooth Newton version for it. So the semi-smooth Newton method has the same structure, but now replace the Jacobian matrix for a Clark generalized Jacobian, which is the convex hull of all the limited of the Jacobians for sequences converging to a point. Okay. So a semi-smooth Newton method was proposed for this equation in Brugnano and Casuli in 2009. They propose this subdifferential for the positive part of X, which has expression of the diagonal of the sign of the positive part of X, which is a diagonal matrix having zeros on one on the entries, depending on the sign of X. Okay, so having this expression, and also having the property that the positive part of X is equal to this matrix times X, we can have this simple form for the semi-smooth Newton method. Okay. Now, it has been proved convergence theorems for this iteration right here, specifically norm condition ensuring the uniqueness and the existence and the uniqueness of the solution, and also the Q-linear convergence for the iterations. Okay, and also has been proved for matrices positive semi-definite under the same condition, but a little bit weaker norm conditions, having the same result. Okay. So after numerical experiments made in the literature, a conjecture arises, saying that for positive definite matrices, the semi-smooth Newton method is going to have global convergence for the solution which exists and is unique. So in the first work, we found a counterexample. We found this matrix T and this matrix B, and we showed that the semi-smooth Newton method cycles between these 3 points, X, Y, and Z. So this problem motivated us to propose 2 alternatives based on the well-known and widely studied Jacobi method and Gauss-Seidel method for linear system. So the idea here is try to solve the Newton system, the original Newton system, but instead of solving it directly, we use the decomposition of the matrix, and for the Jacobi-Newton, where we call it Jacobi-Newton method, we use the diagonal, and for the Gauss-Seidel method, we use the lower triangular. Okay, so naturally, we generalize the conditions, the well-known conditions, the strong diagonal dominance, and also the strong Sassenfeld conditions. So we define this, we said that T, a matrix T, is a strong diagonal dominant if it satisfies this condition, which is very similar to the classical one. Instead of we have an additional 1 here. And also for the Gauss-Seidel method, we define the strong Sassenfeld condition, which is basically the same, but now also with an additional 1. Okay? So under this condition, as we expected, we can prove the existence and the uniqueness of the solution for the piecewise linear system. And also we can prove the global convergence for this equation of the Gauss-Seidel Newton method. So we can make numerical experiments. So as the summary until now, we have 3 alternatives: the classical semi-smooth Newton method, the Gauss-Seidel Newton method, and the Jacobi one. So we make comparisons. So here we have 3 performer profiles for 3 different dimensions, 1,000, 5,000, and 10,000, where we see that for higher dimensions, the 2 proposed alternatives can have very good results. Obviously, these results are related to the structure of the problems that we made. So we make experiments for dense matrices and also for sparse matrices, where the Gauss-Seidel method showed very fast, very high efficiency. Sorry. But we also make another application where we see that the semi-smooth Newton method can be faster. This is the Besnetsk, sorry for the pronunciation. It's a partial differential equation involving the height of the water, in this case, of a phreatic aquifer with a leak at the bottom. So the discretization of this equation results in a piecewise linear system involving the non-negative portent. So we can solve it. So for the comparison, we use the Gauss-Seidel method and the semi-smooth Newton method. For both methods, we successfully solve it. These are the level of the water at each day, and these are the results. So we made 3 grid size, and the results says that the semi-smooth Newton method is incredibly faster. Well, incredible, but do you understand? Needing at most 3 or 4 iterations, and Gauss-Seidel method needed almost 20 times the time of the semi-smooth Newton method. So the conclusion is that for some particular instances, some structures, the Jacobi and the Gauss-Seidel alternatives can be competitive, but for this type of application, the semi-smooth Newton method shows fast convergence. So this motivates us to keep using the semi-smooth Newton method for generalized problems. So the idea here is, since we have a piecewise linear system that is related with a quadratic programming problem, now we want to have another conic projection equations related with more general optimization problems. So the first step is studying the quadratic conic programming, which is minimizing a quadratic function over now a general conic constraint. For this problem, several properties has been generalized and studied, and numerical experiments were made for the particular case of the second order cone. Okay, so the conic projection equations here is similar to the ones before, but now replacing the positive part of x with the projection of x onto this cone, and the projection equation applied to the quadratic conic programming resulted in this one right here. Okay. So here we have the first main result here in the work that says that every solution of the conic projection equation, generate a KKT point for the quadratic conic programming, but also we found that solutions of the KKT conditions of the problem generate solutions for the conic projection equation, So we found that the KKT system is equivalent to this conic projection equation. So now we can study the problem only by using these equations. Okay, as we expected, since the problem has similar structures, the semi-smooth Newton for this problem now it has basically the same structure as before, the same expression, but now we change the matrix B by a generalized Jacobian. And the semi-smooth Newton method applied for the quadratic conic programming is this one here. So we have an expression. And also we could generalize the previous global convergence theorems for the non-negative portent, now for the general cone, also having non-constraints, non-conditions on the matrices, on the data of the problem, having Q-linear convergence, and obviously existence and uniqueness of the solution. And also for positive definite linear operators, we can have the same result, but with a weaker norm condition. Okay? So we have now a conic projection equation related with the quadratic conic programming, but we want more. We want to generalize it to a problem with constraints, additional constraints. So now we're studying the quadratic problem with linear constraints, with minimizing a quadratic function over a linear constraint, and also conic constraints. So the first order optimality conditions are this one right here, involving optimality, now the feasibility of this linear application, and the complementarity for the variable and the Lagrange multipliers. So the idea now is try to find a projection equation related with this problem. Okay, so the previous equation we have is the first one here, and we successfully generalize these equations to a system of equations, now involving this linear constraint. So the first component of this equation involves the optimality of the problem, and the second involves the feasibility of the problem. So we can have now a problem to solve, for example, apply the semi-smooth Newton method to solve it. That's the idea. So regarding the properties of this new equation, we see that this new system of equation can be written with the same structure as the first one. So all the results that we have for the problem without linear constraints can be applied for this new equation. And instead of using the matrix Q, now we use this bigger linear operator involving the matrix Q and the linear application A. Okay, so as I said before, we can apply all the previous results, and we can apply the semi-smooth Newton method. So we have the system of equation, we can solve it now. The semi-smooth Newton method has this expression right here. So we can make now numerical experiments. So we focus on the nearest matrix type problem. So this is a well-known class of problems, which is minimizing the Euclidean distance of a matrix to a fixed metric G with linear constraints. And now the conic constraints involve semi-definite cone. Two important indices studied is the nearest correlation matrix, which is the particular case when this linear application A is the diagonal, and the double stochastic metric, which the linear application is the sum of the entries by row and by column. So the constraint is that sums are equal to 1. So we're focusing on the nearest correlation matrix problem specifically, but the important here is for these two instances, the method proposed in those papers use the same approach. They try to solve this equation here, F. Okay. So for the numerical experiments for this method proposed here, we focus on the nearest correlation matrix, which is the same problem with the diagonal linear system, diagonal linear constraint, sorry. And the projection equations for this problem are this one here, and also the semi-smooth Newton method results in this expression at the bottom. So we can make experiments. The main difference is the expression for this matrix B, this linear operator B. Malik and Sendov in 2006 found this expression involving the Hadamard product and this matrix omega. This matrix omega is a block matrix, which in the first block has a matrix full of ones, and the last block is a matrix full of zeros, and the operand lower triangular blocks has these expressions involving the eigenvalues. Here we propose a different expression for this matrix B, involves just matrix multiplications, and this matrix D is this is a diagonal matrix A. Sorry, it's a diagonal matrix with the sign of this positive part of the diagonal of the eigenvalue source. So with the comparisons, we use the semi-smooth Newton method, Newton method proposed by Key and Sun in 2006, and they use this generalized Jacobian found by Malik and Sendov in 2006. And for the linear system, they use conjugate gradients. We also compare with the QSDP null method proposed by Lee et al. In 2018, which approach is using a augmented Lagrangian method for solving the dual problem. And for the subproblems, they use a semi-smooth Newton method combined to a conjugate gradient iteration. Here, our approach is to use this simpler expression for B and take advantage of the diagonal constraint obtaining diagonal linear systems. So we made 4 experiments. This is one of them, where we compare with made performance profiles comparing with the Key and Su method, where we see that for higher dimensions, the semi-smooth Newton proposed here can be efficient. For the other problems, the Newton method by Key and Sun was faster, but the QSDP null for most of the problem was slower than this method here. So it's basically in between. Okay. So now finally we can address the nonlinear conic programming problem. So as a summary, we studied the quadratic programming problem using the piecewise linear system, the quadratic conic programming with additional linear constraint and we found a projection equation system. And now we want to do the same for the general nonlinear conic programming. So remembering the KKT conditions for this problem and this one right here. Okay, and before presenting the equations, we noticed that most of the results here involve just convex and closed cones. Okay, but for the numerical experiments, we use the non-negative Orton cone and the semi-definite cone, which are well-known cones are symmetric. So it has a lot of properties. Here, one of the applications that we made involves the circular cone. And this is a slightly different cone because it's non-symmetric, because it lost the self-duality. That motivates us to define these generalized implicit cones as the image by a linear replication of a symmetric cone. So for example, we have important instances where we can recover the classical cones, but also we can addition the circular cone. So for example, we have the non-negative Orton, the second order cone, the semi-definite cone, and now the circular cone. So now we're presenting the conic projection equations. So we successfully generalized these equations. These equations has two components. The first one involving the optimality conditions of the problem, the second one involving the feasibility. And we could prove that the solutions of these conic projection equations generates by projecting on the respective cones a KKT point for the problem, and also first order optimality condition points generate solutions of this system of projection equations. Well, so we can recover problems studied before for particular cases. So for example, when G, this function G is equal to the identity, we can have these projection equations which is very similar to the piecewise linear system, and we can recover, we can generalize actually some results. So for example, the uniqueness, the existence uniqueness of the solution, we can prove it by not using the matrix Q, but now using the Hessian of the function f. And another particular instance is when we have two conic constraints, one involving the metric, the function g, and the original variable x. So for this case, we have also conic projection equations here, where when we are projecting onto the cone C and the dual cone of K. And with this problem covers the previous quadratic problem with additional linear constraints when G is linear and K is the cone equal to the 0, for example. So in fact, it's a generalization. So now, since we have the equations, we wanted to solve it. So for this, we define the function h, which is the projection equations. And to measure the improvement for the method, we define this function theta as the norm of this h. Okay, and one of the main properties, one of the key properties for proving the local quadratic convergence of the semi-smooth Newton method, it's the strongly semi-smooth of the functions involved. We successfully proved that the projections and therefore the function h and theta are strongly semi-smooth for these generalized implicit cones. So we can prove we can have this important property. So now the semi-smooth Newton method for these equations has this structure right here. And the first question is natural, is when this, what happens? No, if this system has solution, that's the question. So we can have both cases, a singular system and a non-singular system. When it's non-singular, when we solve the original Newton system, but when it's singular, we propose this perturbed least square, which is the classical least square system, but now with an additional component, additional parameter, which could be any positive, but we use this square root of theta because it's going to be useful for the convergence, and also uses the gradient of the function theta. So for both of the directions defined by the singular and the non-singular Jacobians, we have that are descent directions. So actually generating these directions, we're going to decrease the function. And since we want to avoid the cycles that we found for the first case, we use this globalization technique, which is the well-known Armijo line search. Okay. So for this one, we have an important lemma proved by, in Key and Sun in 2006, saying that if these directions are not only descent direction, but are also satisfy this boundary constraint, at some k, we're going to have Armijo line search with step size equal to 1. So at some point, we're going to have the pure Newton method. And we successfully proved that both of the directions proposed here satisfy these boundary conditions. So now we're presenting the local quadratic convergence of the semi-smooth Newton method presented here. So if we have a solution and we have bounded Jacobians, if the semi-smooth Newton method generates a sequence convergent to the solution, then it's going to converge quadratically when it's close enough to the solution. Well, so the algorithm is, as a summary, is this one. So we need the initial parameters, we need tolerances, we need maximum number of iterations. So we use a certain tolerance, and the first option is always to solve the Newton linear system, because checking the singularity, for example, by determinant, it could be inefficient. So the idea is try to solve the regional system when we are going to obtain a direction D. So by some criteria, we accept it or we deny it. This criteria is basically checking if this direction is a descent direction and if big enough. If one of these conditions are not satisfied, then we're solving the perturbative least square system. Then obtaining the direction, we use our Armijo line search, and then we iterate. Okay, so we have three important details for this semi-smooth Newton method. The first one involves the starting point. For our numerical results, we start with the starting point equal to 0. This point gave satisfactory results, but for other points can found stationary points that are not optimal. So one alternative is the one recently used by in these three papers, when they use an ADMM technique, where they try to solve the problem, and if cannot solve it, they use the final iteration as a starting point of this main method. The second detail is how to choose the subdifferential B. So we have a well-known expression for the non-negative orthant, the second-order cone, the circular cone, and the semi-definite cone. But we saw that as alternative for the nearest correlation matrix, we can have good results using another expressions. And the final one is how we deal with the stationarity of this function theta. So sometimes the semi-smooth Newton method stops on a stationary point, but it could be non-optimal. This happens when the Jacobians are singular. To deal with that, one idea is to notice that the function h that we're using has two components, one involving the optimality and another one involving the feasibility. So the residual function, which is the norm of this h, can be decomposed in two components involving the optimality and the feasibility. and also the gradient can be stated like the sum of these gradients respectively. So in some cases, these both gradients related to optimality and feasibility can be zero. In that case, we said that this point is strongly stationary. So sometimes in our numerical experiments, the semi-smooth Newton method stop at this point. And how to avoid this point is an open question yet. But when we have stationary points that are not strongly stationary point, one idea is to use the perturbed least square system. But instead of using the gradient of the function theta, we use, for example, the gradient of the feasibility. So the resultant direction here for this system is going to be a descent direction for the feasibility, and maybe, hopefully, we can escape from this stationary point. So now, finally, we can make numerical experiments by presenting specifically for linear conic programming. This problem is well known, is minimizing the inner product of a fixed vector C subject to linear constraint and conic constraints. And now, since we already have conic projection equation for this problem, we apply it and obtain these equations. And also the semi-smooth Newton method for these projection equations is the one defined at the bottom. So we make two numerical experiments involving two problems. The first one is the circular cone programming, which is related with second-order cone programming, where we substitute the cone by this simplicial cone with respect to the second-order cone. So the circular cone now depends on an angle and is the image of the second-order cone by this matrix M. So since we can change the angle, we make numerical experiments for different angles. And as a comparison, we use the smoothing method proposed by Tang and So in 2022, which, since it's a smoothing method, they try to solve this nonlinear system of equations. Well, the three first components are linear, but the nonlinearity is due to the smoothing function phi. And they apply a semi-smooth Newton method for solving it, where they actually apply a Newton method for solving it because this smoothing function is always differentiable. So we made numerical experiments. So we run, in this case, 10 problems for different angles, for different starting points. And we see that the residuals are very satisfactory. We use tolerance up to equal to 10 to the minus 8 to minus 6, sorry. When we have very good results involving the residuals, but at the times we can see the consistency of the semi-smooth Newton method. So the smaller the angle, the TC method, which is for Tang and So, needed more time in seconds, while the semi-smooth Newton method stayed consistent for every angle. And for the last angle, both of methods didn't converge. So, as I said, we test different starting points. We present the table using the node vector, but also we have an interior starting point, a randomly generated point, and the point, the starting point equal to the vector full of ones. So for this particular vector, the semi-smooth Newton method didn't converge, founding strong stationary points, but for the other method have similar results as the null starting method. So the conclusion is that in general, this semi-smooth Newton method can be very efficient. And finally, we made numerical experiments for the semi-definite programming, which is a linear programming now, where the inner product is the trace of the product of these matrices. And we focus on the max good problem, which is a semi-definite programming with the diagonal linear constraint. So for this problem, we compare to the SDDP now plus method proposed by Yang et al. In 2015. And the approach is to use an augmented Lagrangian for the dual problem, and at the subproblems, they use a semi-smooth Newton method for it. So we compare for low dimensions, showing that the semi-smooth Newton method has very good results involving residuals and times. We increase the dimension to 10 now, again having a satisfactory result, but we see that the semi-smooth Newton method becomes a little bit slower. So unfortunately, for bigger dimensions, the semi-smooth Newton method could be slow. And the main reason is the implementation. So since we have now not anymore a matrix vector linear system, we have now a tensor matrix linear system, we cannot apply classical methods. So one of the implementation that we did here is to use symmetric vectorization of the matrices. So since the matrices involved in here are symmetric, we save only the upper triangle. And the problem is that generating this subdifferential, this Jacobian, we need to evaluate these in the canonical basis of the symmetric space. So the bigger the dimension, the more time it takes. So one alternative to deal with this that we're implementing right now is the one proposed by Liang et al. This year, which consists in additionate two parameters involving optimality and feasibility, this epsilon opt and epsilon phys, controlling the singularity of these block matrices, and this system can be reduced to an m by m matrix system, where m is the number of the constraints. So this could be very efficient if we successfully address it. So finishing, the contributions of this work are the generalization of projection equations for the nonlinear conic programming, starting from the quadratic programming problem, and we prove also the equivalence to the Kakati system. For the particular case of the non-negative Orton cone, we propose two iterative methods as alternatives, presenting sufficient condition for the existence and the uniqueness of the solution, and also global convergence under cycle conditions. And we generalize properties, well-known properties for cones, for symmetric cones, to generalize simplicial cones. This is an important step. And finally, we adapt the semi-smooth Newton method for the general conic projection equations, showing the local quadratic convergence and obtaining promising result for the circular order cone and for low dimension of the semi-definite one. And as a future work, we are trying to obtain global convergence under weaker conditions and also try to avoid the strongest stationary points and improve the implementation for the semi-definite programming. So the idea is try to solve this problem that we have with the vectorization to having an efficient method, because the good result for low dimensions can be improved significantly for higher dimensions if we can address this problem right here. And that's it. Thank you very much for your attention. And now questions, corrections, and suggestions are more than welcome. Thank you.
Thank you, Nicolas, for quite nice and clear presentation and right on time. So let's start the question. So Professor Defeng Sun, thanks again for participating in this committee. So please go ahead.
Thanks, Gabriel, and thanks, Nicolas, for a wonderful presentation. I know this semi-smooth method very well. I'm happy to see that you are develop new approaches for using semi-smooth methods. So you use projection equations, but it seems to me that it is also called Robinson's normal equation. Is it true or not true? So look at your called projection equation, right?
Yeah.
For the variable at the very beginning of your talk, it seems to me it's just normal equation.
The first form.
Yeah, first part. I think it's go to quadratic programming. Let's go to quadratic programming. Yeah, I love yeah. Okay. Yeah, here you can see here you got a projection equation for QP, right?
Yes.
But Stephen Robinson has introduced a notation called the normal equation.
Yes.
I think it should be part of a normal equation.
Yeah,
this is well known in the complementarity version in quality society. We call normal equation, but it's okay to call the projection equation as well. This is a comment. Now let's go to page 43.
Where? I'm sorry.
43 slides.
43.
Yeah.
Yes.
Yeah. So here you use this theta, right?
Yes.
Now you prove that theta is strongly semi-smooth. First of all, normalized, do you assume theta is continuous differentiable or not? It's not, right?
I'm sorry, I didn't hear.
Do you assume that theta is a gradient, is a continuous differentiable or not? So you can look at the last line, you have normalized theta.
I'm sorry, I'm not understanding. Sorry.
So sorry, is theta continuous differentiable? Is theta smooth?
Theta.
Yeah. So the function, so the
No.
residual function, is the residual function smooth?
Okay, so let me check if I understand. The question is if this theta function defined as this one is smooth.
Yeah. Is theta smooth? So that's why let me type my question.
No, it's not, because if we are
okay.
using this
then
function,
why you have a normalized theta there?
Why we have? I'm sorry.
Yeah, why we have why we have
Nicolas.
the gradient, right? The normalized theta.
Nicolas, ele está perguntando se essa função θ tem derivada. E aí,
I think
so Nicolas, I want you to check the definition of strongly semi-smooth of the last line. I think it should not be.
I think I understand you. Your question is about the notation.
That's right.
Because I use the
not
gradient.
only about notation. I think it's not the gradient should not be as theta. It should be as theta x plus wx, lambda plus w lambda.
Yes, I mean, yeah.
I think that's the typo, right?
I think I understand the problem. I use that notation because it's usually used, but I'm aware that this is not the gradient because this theta function is not differentiable, so it should be the differential. Actually,
it's almost everywhere differentiable, right? Okay.
Yes,
that's okay. But the point should not be at the fixed point. Should not be at x lambda, right? It should be the gradient at x plus wx, lambda plus w lambda. So can we go back to the definition of semi-smoothness? The first several pages, Nicolas.
Yeah, I'm thinking. Can you repeat the question, please?
So let's go back to the definition of strongly semi-smoothness.
Yes.
So when we use the definition, the gradient or the generalized gradient should be taken at a moving point, not at the fixed point.
Yes. Yeah, that's true.
I think this is typo here, right?
The strongly semi-smooth definition is punctual, and a function is called strongly semi-smooth if satisfies the condition for all the points. basically.
Yeah. So let's go to definition. Can you go back to the definition of strongly semi-smoothness? Let's the slide number 5 or 6 or something like that.
I don't have the definition here.
Semi-smooth. Do you have a definition for semi-smoothness?
I have it, but let me check the PDF document.
Yeah. Okay. Let me type.
I don't have it right here. Sorry.
That's okay, because I think this is something I don't understand.
So check right here.
So, Nicolas, can you look at the chat window? I typed the definition of strongly semi-smoothness. So the Jacobian should be taken at x plus h, not at x.
Yeah, I think I understand.
That's right. I think for your page 43,
Yes.
your nominal gradient should be
now I
the
understand.
moving point, right?
Let me check this. I'm sorry.
That's okay. That's okay. You
Here.
can go back. Yeah.
Yeah.
That's right. 43. You can see.
I mean, the strongly semi-smooth definition involves the first one involves the directional derivatives
That's right.
in the direction of h.
Yeah, we ignore the direction derivatives. So that's the key point. That's the key formulation now. So here in 43, you take the nominal theta of the gradient at x lambda. It should not be at x lambda. It should be at, let me type. Should be.
Yeah, it should be x plus w.
Yeah, that's right. I think you got one point, right?
Yeah, I understand now.
That's good. I think there's a typo, right?
Yeah.
Okay, that's great. I think, Gabriel, I don't have other questions. Very good. Thank you very much. Thanks, Nicolas. Gabriel, I leave to other panel members. Yeah.
Thank you very much.
I seen your thesis, Nicolas, that you are using the wrong definition. So maybe you should look into this deeper, if it is really a typo or if we are missing the point here.
Okay. Yeah.
Thank you, Professor, for the.
Thank you very much.
So now let's maybe go to Professor Nathan Krislock. So Nathan, thank you for accepting the invitation. Please go ahead.
So let's see. I made a number of notes in the thesis that I can send to you.
Okay.
There's just a number of typos I found.
Okay.
For example, actually your counterexample, I was surprised that the counterexample on page 13 of your slides, I was getting different numbers. it was still a cycle. It was definitely cycling among 3 points, but the x and y vectors that you put in your paper and also on the slides, I was getting different values, for example.
Okay.
So that's a minor thing.
I'm going to.
Let me just see. So I guess my major concern is, you know, when I got to the end of the thesis, I got a sense that that the final part of the thesis maybe was a bit rushed and unfinished. You know, like maybe I got a sense that you really need to graduate now, and so let's just go with what we have. And but you clearly stayed in a number of places where it's like, this is a work in progress, there's many things I still want to do, and
Yes.
so on. And I found especially the max cut results to be very underwhelming, like when you're restricting yourself to n equals 3 or n equals 10.
Yeah.
This is like, this is sending off all sorts of alarm bells. You're like, okay, something bad has happened here. His numerical results have not worked out at all for some reason. And I guess my suggestion would be that maybe you shouldn't push everything in there that you have at this moment. Maybe there are things that are best left out for now, because it's really not finished.
Yes. Yeah. The idea was to finish the numerical experiments but we actually were comparing numerical experiments from another paper, which uses a database. So the dimensions for this problem were 800, 2000, 3000, and we tried to solve it. And actually, we're trying to solve it until now. But the implementation issues that I think that's the main reason arise these problems with the dimensions.
Yeah, you may want to consider just, bailing on that material. Like, my understanding is the first paper can't really be changed because that's already been accepted and published. The second paper is under revision, so that's, not much we can't really change a lot there. I guess, it'll get changed through the revision process.
Yes.
But the final paper, yeah, you might want to pull back some of that material and wait until it's ready before adding it.
Yes.
Just to make sure the thesis is coming off as strong as possible, and
Yes.
not leave that sort of feeling like, oh, it looks like they're rushing at the end here. And
Yes. Yeah.
I guess maybe another question I had that you didn't really talk about in your presentation was the fact that these simplicial cones could be not closed.
Yes.
And I noticed in your thesis you mentioned that there's an assumption that you can make. I forget exactly what it is, that if this holds, then this simplicial cone will be closed.
Yeah, we have to when the linear applications, the null space of this linear application touches the cone only on the vertex 0, and the other one is when the null space crosses the cone in the interior. In both cases, the resultant cone is going to be closed.
So you make the assumption that the simplicial cone is closed, but I wondered why not use those other assumptions, like use one of those sufficient conditions for it to be closed.
Yeah.
And I also wondered in the proofs where this became important, that the cone is closed. Did you just assume the cone was closed, or did you make use of these sufficient conditions instead?
Yeah, so from the preliminary, we studied the simplicial cones. We studied the sufficient conditions for the closeness. And at some point, we assume that from that point to the end is going to be close, because we can ensure the existence and the uniqueness of the projection onto this type of cone. So that's the main reason. But we didn't use these assumptions because it could be restricted, because there are cones, there are linear applications that the null space touches the cone on the boundary, and also the resultant cone can be closed or cannot be closed. So since we don't have a characterization of the closeness of this resultant cone, we thought it was clearer to use the state assumption that is closed directly.
I see. Yeah, those are all my questions for now. But I did want to say, you know, I did found the thesis to be very well written and carefully typed. It looks very nice. So thank you. And nice
Thank you.
presentation as well.
Thank you very much.
Thank you, Nathan. Thank you for the suggestion. So, Nicholas, maybe we should consider removing this max cut part from the thesis. I think it's a interesting
Yes.
advice.
Until complete the numerical experiments, maybe it's better to keep it out.
So next, Leandro Prudente, thanks for accepting the invitation. Please go ahead.
Thank you, Nicholas and Gabriel, for the invitation. Can you hear me?
Yes.
Yes. Congratulations, Nicholas, for your presentation. It was very clear.
Thanks.
And as far as I was able to read the thesis, it's very well written too. I was already familiar with the first part of your work because I have participated in your qualifying exam. And I'm happy because I see that since of the qualifying exam, you have done a lot of work. And I was happy to see that a comment that I made during the qualifying exam, I think that motivates you to include an errata in the first part of the work. No?
Yes.
However, I believe that you should to include the correction in your thesis, in the text. You put the errata, but didn't correct the theorem. No? That you have to the diagonal have to be positive, no, in the first part of the work. So I suggest to include the correction in the test, no? Not only to make a errata. Okay, and I have only one question. Can you show can be for the first part of the work, the iteration scheme?
Which one?
Can be the first, the linear system.
The semi-smooth or the Jacobian Gauss?
Yes, here.
This one, okay.
No, Jacobian Gauss, no, this is the Newton method. For the Newton.
Newton method, sorry. This is one here.
So in each iteration, we have to solve a linear system.
Yes.
With this matrix, V plus T, no? And V is a diagonal matrix, no?
Yes.
And so the difference for one iteration, the other iteration, one subproblem and the other subproblem is only the diagonal of this matrix, V plus T. Now, assume that you have decomposition of matrix 3. For example, a Cholesky decomposition or LU decomposition. Can you use the acknowledgement of this decomposition to solve this linear system, or you have at each iteration to make a new decomposition of this matrix, V plus T?
So the question is, okay, so the idea is try to use the semi-smooth Newton method, but now assuming that we have a particular structure of the matrix T. So for example, if T is positive definite and we have Cholesky decomposition.
Yes.
If we can take advantage of that, that's the question, right?
Yes, you have to make this decomposition only once.
Yes.
Because T does not change. So it's possible, and you have the decomposition of T, and you add a diagonal matrix. It's possible. Is it possible to use the Cholesky decomposition or LU decomposition to solve this linear system?
That's a good question. I didn't check. I didn't study assumptions, any other assumptions of the matrix T, and but now thinking here, maybe, because for example, for this case, we have a diagonal matrix, and if we have a Cholesky decomposition, maybe we can decompose the matrix as well, and maybe we can take advantage. But I didn't study. I didn't check it actually.
I think that in the second part, for a general cone, you have the spectral decomposition of V. No? Yes?
No,
when the cone is the cone of the symmetric matrix, no? Symmetric and positive definite matrix. You have the spectral decomposition of V.
Of X, actually, the variable, not of the matrix.
But how you construct the matrix V in the second part?
No, I mean, when we generalize to a closed and convex cone, when this problem right here, the equation is this one right here. So this matrix T now is not, that could be not a matrix.
No, it's not.
It could be a general linear operator, because this cone lives in a space that could be general.
And in your numerical tests,
for the numerical test, here, for example, we use dense matrices T. So this is the experiments changing the matrices T. So we made dense matrices, sparse matrices with different percentage of sparsity, but not necessarily positive.
When the cone is the definite positive, this T.
Now, for the particular case of the semi-definite cone, this matrix T, if you looking at these equations, using the data of the problem, arise here the inverse of T, basically. So this matrix T is no longer with the variable X, it's now with the projection of X.
Yes.
So now this matrix is the data of the problem. So this Q is a general linear application, and it's not anymore a matrix itself, even for the semi-definite cone. Because the semi-definite cones are matrices, so the linear applications are taking matrices, two matrices, and therefore this Q is a tensor.
Okay. Yes, you're right. My question only is applying the first, I think the first part of the work is that if it's possible to use the acknowledgement of the decomposition of T so more efficiently the linear system. Okay.
Okay. Yeah, I understand.
Yeah.
I think it's a good suggestion. Thank you.
Yes, thank you, Leandro. It was really a nice suggestion, and it's something that we have not thought before, like how to use the work of the previous iteration in the next one. So maybe we should write this down as something for future research. Okay. Next, Professor Paulo Silva, thank you for being part of the committee. Go ahead.
So thank you, Gabriel and Junior, for inviting me to, and Nicolas for inviting me to the committee. I have first to say that I believe that Nathan is right. You should carefully think what you want to keep from the last part of your work, because it's a kind of rush. So actually, if you read it at least twice, I had the feeling that two paragraphs in sequence, they were basically the same paragraph that you were trying to write in different ways, and they were left there. So I have examples in the text, like you read a paragraph, the next one says basically the same thing with different words and a little bit different structure. So I had this feeling that you were typing and, okay, let me think how to rewrite this again, and then it was left there. So you should think a lot about what is better to keep and what is better to leave out, especially the numerical part. Maybe it's better to leave out. But because the reason for this is that all the rest of the thesis is very well written, and the results are so nice that it's like instead of ending in a boom, instead of ending in a high note, you start ending in a low note, which is a kind of odd. So you should consider that. Okay. People have already asked some questions. I will just pose two questions that got me more interested, especially in the beginning of your work. The first question is, how did you come up with the cycling example? Because the numbers are not, I don't know, natural to me when I look at it. So maybe what was the reasoning? What made you create that example? Because it's not really a numerical example. It's not like something that came out of numerics, I think. I think you were thinking, what was the thinking process to get that result?
Well, actually, it was from the numerical experiments. I tried to run as much example as possible, and sometimes we came up with experiments that satisfied, and then I check it exactly, and then we found that example. So
it was basically random examples, and you found some cycles, and then you said, okay, this example is basically 32 instead of 32.34. You try to get to more whole numbers in some sense, right? Okay. So now it makes some more sense to me. And another point, I think I have already said that to you, maybe in a seminar or something like that, but I like this thing. Go to your performance profiles for random matrices that you have for the first case. For the first work. So there. So this is the example why I don't believe in random generated matrices. Because if you look at your performance profiles, especially for the larger one, the 5,000 and the 10,000 cases, okay, you see that what you're seeing there is just that you're solving the same problem over and over again. Even though they are randomly generated, those matrices with random entries, they have very special properties that they are just converging to a specific problem. If you increase the dimensions, the overall structure of, I don't know, of the eigen values and many properties of those matrices, they just become the same. So that's why, for example, in your 10,000 example, the largest one, you see that basically you have like a flat and then a bump and then another flat. You see, like, so it's, if you look at the Gauss-Seidel, it's flat, basically 0, and then go up to 1 at once, and then it's remain at 1 forever, you see? And the same for the semi-smooth. It's just 0, and then after 3.7 is go to 1, and it's 1 again forever. So this fast transition is basically that you're solving only one problem over and over again, and what you're seeing there is just basically random noise. So even though you're solving many problems, the overall structure of the matrix is always the same.
Yeah, I understand.
So you present a performance profile that give this impression that we're basically solving many problems, but we're not solving many problems from the numerical point of view. You're just solving one problem many times. So this is just an example why random matrices and random problems, unless you know exactly what you're doing, they can be very tricky. You can think that you're doing many things and you're only doing one. I have already seen that in many papers. So usually I don't like, if I am the reviewer, I usually complain a lot about random problems. And if I'm writing a paper about something, Junior knows that because we are in that situation right now, I usually try to avoid random problems. And that's a good thing in your case because you also had those non-random problems just after that, the water dripping cases. So that was important.
Yeah.
But
for example, if we want to make random experiments for this problem, what would be a good suggestion to change to generate it randomly, but changing the structures for set problems?
Maybe we have to change the structure of the problems in a more structured way. So, for example, instead of choosing all the entries randomly, we first choosing some entries should be random, the other ones should be something. And then the random, you see, you have to get structure. Usually I try to find problems to solve instead of using random problems to test because random problems to test is cheap and easy and we like them because they're cheap and easy, but they are, I don't know, they don't give the right picture.
I understand.
I don't like them because they don't give the right picture.
Yeah, that's a good observation. Thanks.
Okay. So be careful with those, especially in the future.
Okay.
This paper already published, but in the future, be careful. Okay. So that's another question. Let me see if I have anything else to say. Not really, I would say. I will just want to point out that I like it a lot to work because you had this program where you decided, okay, I'm going to work with those characterization of KKT systems using projections for a very simple case first, or get something out of it, and then from a little bit more complex case next, and get something out of it. But you know where you're going to, you know where you're heading to. I like this idea of having this program and going through it slowly. It's a very good way to do your research, and I congratulate you and your advisors for that. I remember another small detail that I'd like to point out in this Jacobi-Gauss-Seidel method. You were comparing with Newton, but Newton, if understood well, you are solving the system, right? So you're solving the system using a factorization.
Yeah.
So this can be in the first case. So in the Gauss-Seidel, so you're solving the system using a factorization. So, and while for the Jacobi-Gauss-Seidel, you're never really solving any system, you're just stopping with some stopping criterion, 10 to the -5 or something like that. So if you're accepting that, maybe you should try to solve this Newtonian systems, the Newton system, instead of using a factorization, using an iterative method like CG or something like that. Because in this case, maybe you can speed up a lot this partial solution of the Newtonian system. And if you look at the other applications of the semi-smooth Newton method for large-scale problems that you saw during your thesis, that you saw in the literature, in many cases, they were solving the Newtonian system using an iterative process.
Okay. So the suggestion is, if we are going to try to solve the system, instead of changing the linear system to using this composition, try to propose another method to solve the original linear system.
It is more to compare fairly. Instead of comparing something which is not really solving any linear system at all, basically it's just solving systems that have triangular matrix by definition. with something which is actually solving a linear system, which is large scale and is sparse and have to do many things, instead of trying to do that, maybe you should just try to solve the linear system using also iterative method. And then you can stop with a reasonable precision and have fun, find out which is precision, the precision that you need to get the final precision that you want in the end. But maybe this would be more fair, you see?
I understand. Yeah, I understand.
See, because
You're saying that basically we are doing too much work at each iteration by solving the linear system until we are very satisfied with it. Maybe we should use like an inexact Newton method and be more loose on how we solve
yes,
the sub.
yes, like a truncated Newton. Instead of using a really Newton in the first case, I'm talking about the semi-smooth case where you're solving the system. You might want to consider using a truncated Newton method instead of a pure semi-smooth Newton method, because I think it's like comparing apples to oranges. Like you compare something that you're gonna get you a full precision solution at the end with something that only can get you a rough precision in the middle. And you're saying, okay, the full precision is much slower, but it's full precision, right? Why the other one will never be full precision.
I understand. Yeah, I understand.
And another little detail, Jacobi and Gauss-Seidel is something I like a lot because it's a very good example of which one is the faster. For example, in your performance profiles, you would say that Gauss-Seidel is faster, right?
Gauss, yes.
Than Jacobi. But this is actually misleading because Gauss-Seidel is essentially a sequential method, because I have to find the first variable and use it to find the second variable and then use it to find the third variable and so on. So if you want to implement it in a computer, you need to implement it sequentially, while Jacobi is essentially a parallel method. So if you know how to use parallelization, in many cases nowadays where you have many cores and GPUs and things like that in your computer, Jacobi can easily be faster than Gauss-Seidel because each iteration is going to be parallelizable while the other one is not going to be parallelized. Okay.
Yeah,
so this is another little detail that.
Yeah, I mean, the times that we're measuring here is to finding the final solution. I know that Jacobi iteration itself, at every iteration, is faster, but the overall convergence of the Gauss-Seidel Newton was faster. So
yes, I understand.
Those two times, not the iteration time itself.
But the Gauss-Seidel iteration is essentially sequential. So I'm assuming that we're solving a triangular linear system at its step. And the way it's solved, it's not very easy to parallelize. I don't think it's possible to parallelize at all, I would say. While the Jacobian iteration, you are just multiplying matrices. So multiplying matrices can be really, really, really parallelizable. So it really depends how this thing is done in MATLAB, and you have to know how to do it.
Yes. Yeah. No, I did a basic implementation basically. So I know that we can improve that.
So that's my question. Thank you.
Thank you.
Okay, thank you, Paulo. Junior, maybe you want to say something?
No, I just want to add that Nicolas did a very nice presentation. Congratulations, Nicolas. And of course, this last part of the dissertation is the rush. We are still working on the problem. And in general, I'm happy with the work that Nicolas has been done, and it is impressive how he is growing during the years. He is now a different person, a ready PhD student, and I'm very happy with this.
Thank you.
Thank you, Junior. Yeah, I agree. Nicolas really improved a lot during the years, and we can see how mature you are now as a researcher. And Nicolas, he is very persistent and very he's very busy looking at the details of the thing. He likes to investigate things very deep, and this is
sometimes slowly, right?
yeah. Sometimes he does that too much,
Slow.
and it becomes a slow process. But it's a nice quality to have. Only you have to maybe balance it, and sometimes you need to rush a bit more. But I'm also very happy with how you turn out as a researcher, and I'm confident that you will do nice work in the future. So he has a scholarship with Paulo. He is going to start next year. So I'm certain that it will be very productive work.
I hope so. Thank you very much.
So